All right, can everybody hear me up there? We're good? All right. Last time we gave some extra credit problems. Let's try to solve a couple now. Not all of them. The ones that we don't solve are still open bounty. Some of you have turned in solutions, which is great. Prime numbers. Prove that there's no highest prime. The Greeks did that over 2,000 years ago. It's a relatively straightforward argument. Anybody want to give a hint how to start? How many thought about this problem? I'm curious. Okay, a few of you. All right, I'll take that. So it's a proof by contradiction. Yeah. Okay. So assume there's a largest prime. So assume P is the largest. Right? We assume towards contradiction. So if we take, say, P factorial and add 1 to it, by the way, I don't want to be presumptuous. What is factorial? Yeah, it's all the numbers up to that, all the integers up to that added together. Multiplied together, right? So if you add 1 to P factorial, assuming P is the largest prime, that's not divisible by 2. It's not divisible by 3, by 4, by anything up to P, right? Why isn't it divisible by any integer up to P? From 2 all the way up to P. Because of this 1 here, right? The remainder will be 1 if you try to do the division. That's why we construct it this way. So it's not divisible by anything up to P. Does that mean this number is prime? How many say this number, P factorial plus 1, is prime? How many say not necessarily it's not prime? Yeah, it's not necessarily prime. So if it was prime, end of story. That's the end of the proof, right? Because P factorial plus 1 is a lot larger than P, not just a little bit larger than P. But either way, it's larger than P. And if it was prime, there's a largest. P wasn't the largest prime. There's a prime bigger than it, and we're staring at it. But this doesn't necessarily have to be prime, P factorial plus 1. And in this other branch of this logic, the other case, if it's not prime, if it's composite, then what can you say? Yeah, if it's composite, it's got to divide by something other than itself. But it can't be divisible by anything up to P, so it's got to be divisible by something, by some prime larger than P, right? And that would make it, again, the case that there's some prime larger than P, and P wasn't the largest prime, so that contradicts the assumption, the notion that P is the largest prime. So, and that's how it goes. It's a pretty short argument, right? One can write it all out in words. It'll be one paragraph. Yeah. That's an excellent question. I was waiting for somebody to ask it. Why does it have to be divisible by a prime larger than P? Why can't it be divisible by a composite larger than P? And then there's no contradiction again. Very good question. Somebody answer that. Very fair question. Yeah. Yeah, if it's divisible by a composite larger than P, take that composite, break it up into primes, and it's got to be divisible by all these components that factor out together to produce P. Right? It's got to be divisible by all the divisors of P as well as P, right? And one of those better be larger than P. Because it can't divide by anything less than P, because the remainder will be 1. Does that make sense? Let's argue it in a similar but slightly different way. Take this number here, represent it as a product of primes. And you can always do that. There's a famous theorem that has a name that tells you that you can do exactly that for every integer. You can represent every integer as a product of primes. How many believe that, first of all? Yeah. What is that theorem called? It's so important, it has a name, actually. The fundamental theorem of arithmetic. That's what it's called, right? And how do you prove that? Well, divide it by anything that it can divide evenly by, and keep doing that. Eventually, you only have a product of primes if you keep going and going. You may have the same prime over and over again, like 8 is 2 times 2 times 2. That's all right. But 8 is a product of primes, 2, 2, and 2. All right, so represent this as a product of primes. And then if it's composite, it's got to divide by something. And that something can't be less than p, because the remainder will be 1. Okay. Anyway, if you think about it, you'll see that it works out. Let's quickly prove the another prime fact, that there's large prime desert, large blocks of non-primes, of composites, large prime deserts. Sometimes they're called that. So how could you show me, say, 1,000,000 integers in a row, none of which are prime? All of them are composites. Or 1,000,000,000, or a Google. They're larger and larger sections of blocks of composites are there. They exist. Not infinite, because if it was infinite, the first statement wouldn't be true. Okay, so how can you show me 1,000,000 composites in a row?
So we consider arbitrary number n.
Yeah.
We take a consecutive number that is 2 plus n factorial, 3 plus n factorial, all the way to n plus n factorial. And by the associative law of multiplication, 2 plus n factorial is divisible by 2, because n factorial has 2 in its factor. And 3 plus n factorial is divisible by 3, and n plus n factorial is divisible by n.
Yeah.
That will be n minus 1 consecutive integers that are not primes. So we can take any arbitrary number of n, we can have an arbitrary number of n minus 1.
Yeah. So take some large number. In fact, why don't we make this n, I guess. And maybe we'll. I guess we should probably add. Add 2 to that, right? There's various ways of expressing it. But take the range n plus 2 factorial, or even just n factorial. I'm not sure why this 2 is even necessary. But let's say n plus 2 factorial plus 2, all the way up to n plus 2 factorial plus n plus 2. So the range is n consecutive integers, right? From this first number all the way to this second number and everything in between. Each one of those numbers is composite, right? Because this number, this quantity here, is divisible by 2, right? How many can see that? Yeah, because this is divisible by 2, and that's divisible by 2. Factorial is divisible by everything, because it's all the numbers multiplied together. If you add 3 to that instead of 2, it's divisible by 3. If you add 4 to that, it's divisible by 4. How many can see that? If you add n plus 2 to that, it's divisible by n plus 2. Right? And so that long range of size n is all composites. And n was arbitrarily picked. If I picked n as 1,000, I'll have 1,000 composites right there. If I picked n as a Google, I'll have a Google composites right there. So there's larger and larger blocks of composites. Of course, they're further and further down the number line, but nobody said that they're close to the origin, to 0. That's sort of the crux of the argument. Right? You could probably substitute n instead of n plus 2 and make it a little simpler there. Any questions about that? And notice that these two statements don't contradict each other. There's no largest prime, but there's larger and larger and larger blocks of non-primes. Both of those are true at the same time. The size of this block will never get infinite. It'll just be arbitrarily large. A Googleplex factorial, the larger and larger prime deserts, primeless blocks of composites. Okay, any questions about either one of these? Yeah. What's this? Yeah. So this quantity here is divisible by 2. If this 2 was a 3, it'd be divisible by 3. And the next number will be divisible by 4, by 5, by 6. All the way up to here, this number here is divisible by n plus 2. Right? Because this is divisible by n plus 2. This is plus n plus 2. So this quantity is divisible by n plus 2. So all of this entire range between this quantity and that quantity are all composites. They're all divisible by something other than 2. Other than 1, actually, by 2 or something else. None of them are prime, and there's n of them. And n was chosen arbitrarily. Okay. Good. Another quick question. We said if you have a square and you put 5 dots in it, anywhere you want, there is a pair of dots whose distance is 1 over square root 2. How many worked on that one? Okay. Any thoughts about how many got an answer for that? How many can prove it? Okay. Any thoughts about that? And by the way, let me say some meta comment here. If you're not working on problems, we present lots of problems and exercises, and the problem sets are full of them. And if you're not working on problems, you're not going to get any better at solving problems. Seeing other people solve problems is not the same as solving them yourself. And if you're not really sure about how dramatic the difference is, let me put it a different way. Watching people do sports on TV is not the same as doing sports yourself. If you watch the Olympics, it doesn't make you an Olympic athlete, not even close. It has nothing to do with each other. So solving problems and hearing solutions of other people solving problems has almost nothing to do with each other, just like sports. So problem solving is not a spectator sport. Okay, you got to do it yourself. And if you're not working on it, you're cheating yourself. You're selling yourself short. You're not going to get better much. So, all right. Any thoughts about why this is? First of all, I haven't said if it's true or not. Is it true that for every 5 configuration of points in the unit square, there is a pair that's 1 over square root 2 or less apart? How many say true? How many say false as counterexamples? All right, so the majority said true, and the answer is true. You're right. This time the majority is right. Sometimes it's not the case. Okay, so any arguments why that's true? Okay, what do you say? Okay. Okay, so he's saying basically that this is a worst case example is what he's saying. He's saying if you put 4 dots, 4 points in the corners of a square and put the 5th one in the middle, that's about as bad as it gets. And that's square root of 2 over 2, which is 1 over the square root of 2. But let me write that down. So 1 over square root of 2 rationalized is square root of 2 over 2. That's half the diagonal of the square. Right? That's this distance here. How many agree that this is a worst case example? Yeah, and you're right, and he's right. It's a worst case example. How many think we just proved that this is a worst case example? Oh, okay, nobody's raising their hand. And you're right again. We haven't proved that this is a worst case example. We asserted that it's a worst case example, and it happens to be correct. But that's not a proof. Just asserting something and saying that's right doesn't constitute a proof. So you've reduced the problem to proving that this is a worst case example, and now you need to prove that. And that's not completely obvious. Somebody might say, well, okay, in this configuration, if you move any of the points even slightly, you'll kind of mess it up, and the things will get closer to each other. And that's still a true statement, but that's not a proof. It's kind of hand-wavy and intuition. What's that? Again, a true statement, but it doesn't make it a proof. Yeah, he's saying pigeonhole, and somebody else earlier said something insightful. All these are true statements, but let me show you how to settle it decisively. Because somebody might argue, maybe contrary, and argue, well, for this example, okay, that's a true statement. If you perturb the point slightly, you're only going to get better, not worse. Somebody might say, well, what about other configurations where they're here, 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 and here, or some other weird configuration where they're moved apart by, all of them are rotated slightly in the circular direction, and or just some random, you have to cover an infinity of cases, and you're just arguing about one case, not an infinity of cases. So, question or comment? Yeah. So some people are saying already the same thing. So let me show you the argument. So they're saying if you partition this square into 4 subsquares, and then you put the points in anywhere you want, the 5 points. Now what can you say very decisively for all possible cases? At least one quadrant, one of the 4 subsquares, must contain 2 points. Why is that true? 2 words. You want to buy a vowel? Pigeonhole principle. Thank you. The pigeonhole principle. A simple but beautiful and very powerful principle. You put 5 things in 4 containers. One container will have to have 2 things double up. There's no other way. In fact, one container can have 3 or 4 or 5, but at least 2 is the point. If you have 2 points inside a single square, the farthest they can get away from each other is at 2 opposite corners, and that's much easier to see than 5 points in a single square. Now that's decisive. It covers all cases. The pigeonhole principle comes to the rescue. How many see that now? And that's very decisive, very clear, very elegant. It covers all possible cases. It doesn't leave you scratching your head wondering if there's any exceptions. End of story. Okay, any thoughts or comments about that? So let's have some, yeah, go ahead.
Is there any clear proof that this is the configuration that is the pigeonhole principle?
You can prove that this is the optimal or the worst case scenario. It's not easy to do because it's 5 moving parts. There's 5 moving pieces. You got to keep track of all of them and look at all possible other combinations that are nowhere close to this configuration. This argument covers all of them, no matter where the points are. So I'm not saying it's incorrect. You made a good observation. You are even correct. But to prove that, you're not done yet. You need to do some heavy lifting to prove it, and it's not that easy. Yeah.
Seems like in the pigeonhole case, we're still depending on the inside being on 2 opposite corners of the bases. Can we actually prove that?
Yeah, so he's asking another interesting sub-question. Why is it that for 2 points in a single square, the farthest distance is opposite corners of a square? That needs to be proven too. For extra credit, prove that. But that's much easier than your original problem. Okay. The width of a square is its length of its diagonal. By width, diameter, the diameter of a square, diameter is like bring a pair of calipers around the object, rotate them, and the largest separation of the 2 calipers at any point during the 360-degree rotation is the diameter or width of the object. It's like the widest point across the object, no matter what it's shaped like, however irregular it's shaped like. But you're right. That needs to be proven too. It's just a lot easier than the original. For extra credit, prove that. Question?
This 5 point scenario can be easily proven that it is the worst case scenario.
Okay, for extra credit, prove that. But don't just argue that if you move them slightly, it won't help, because you got to show that it's the worst case scenario over all other configurations of 5 points, not just something that's this or a perturbation of this. Okay, but so your proof has got to cover all possible cases, and there's an infinite number of this, uncountable infinite number of them. But for extra credit, if you want to prove that, submit a proof. I don't want to take too much class time on this, except to say that the pigeonhole principle is a discrete principle. It's a principle about integral numbers of things. N objects, n plus 1 objects, n containers, n pigeons, n minus 1 holes. It's a discrete concept, not a continuous concept. The original problem was continuous. The points could have been anywhere. They could have been coordinates, 1 over pi, comma, 1 over e squared, from the origin or whatever. That was a continuous, real numbered kind of problem. But we applied a discrete principle to resolve it. So have some meditation over that Jedi trick. Just because a problem is continuous doesn't mean you can't use discrete principles to attack it and solve it. And vice versa. Just because a problem is discrete doesn't mean you can't use continuous concepts like integrals or whatever to solve that. Often it's matched. For discrete problems, we use discrete concepts or solution techniques or theorems or lemmas. For continuous quantities, we usually use continuous results, quantities, formulas, lemmas, theorems, concepts. But sometimes you can mix it up. So remember that meta solution insight. You can mix and match. And that's an interesting example of that. A discrete concept, the pigeonhole principle, came to the rescue to solve a continuous problem. So kind of reflect on that in your spare time. Any other questions or comments about this? All right. The rest of the problems that are outstanding, you can still get extra credit by submitting them. Let me give you another extra credit problem. This one is more algorithmic. So you have an array from 1 to n, and it has quantities. It has numbers in them, in the array. I don't know, the numbers might be whatever, some integers. Your job is to find the subarray, the contiguous subarray that maximizes the sum. You want to find the contiguous subarray with maximum sum. And you want to tell me where it is. So I give you an array of n integers, negatives or positives or zeros, and you tell me where the contiguous subarray of maximum sum is in this bigger array. How many understand the question? And I'm asking for an algorithm. I'm just giving an example here. So I'm asking for an algorithm. And I'm asking for an efficient algorithm. How efficient, I won't tell you, because that might give too much away. But you tell me, what's a brute force trivial way of solving this? How efficient do you think you can solve this as a function of n for arbitrary arrays of size n? Yeah. So you can easily solve it, in time n cubed. How many can see how? That's just a brute force approach. How would you solve it in time n cubed if this is an array of size n? We haven't talked exactly about big O notation, but we will. I assume most of you have seen big O notation. We'll define it pretty shortly and move on. But how many can see how you can solve this problem in cubic time, n cubed? How would you do it?
So you iterate over all lengths of the subarray and all starting positions.
Yeah. That's right. So you iterate over all I and j, where I goes from 1 to n and j goes from 1 to n, or from I goes from 1 to n, j goes from I to n, I guess. So you iterate over all beginning and ending subarray I and j positions. For each one of those, add up everything in between, and keep track of the running maximum of all these sums. And at the end, you'll know, and that's n cubed, because there's n squared combinations of beginning and ending point. Right, there's n places the beginning point can be, and roughly, for each one of those, there's roughly n places that the end point can be. That's n squared. For each one, you got to add up everything in between. That's another factor of n. So that's an n cubed algorithm. How many can see that? So in n cubed time, you can do it brute force trivially. It's just a few lines of code. Maybe 10, 12 lines. So I'm asking you for something better than that, obviously. Right? Yeah, you can use, but let's not give the answer away, because this is worth extra credit now. until next time, which will be Thursday. Any questions about that? Yeah. If you happen to know an algorithm that solves this and solves this efficiently, yeah, more power to you. Just tell me how it's done. But sure, yeah, cite it. So I mean, don't pretend you came up with it. Cite it, but you still get credit because you've solved it. Just don't tell us now because that'll spoil it for everybody else. Yeah. No, it could be anything. I just highlighted 3 things here, but it could be arbitrary contiguous block. In fact, if all the numbers are positive, that block is what? The entire thing. That block is the entire array. If all the numbers are positive, you just keep adding and adding and adding. The maximum sum will be the entire array. How many can see that? If everything is positive, you just take everything. If everything is negative, what's the solution? There's 2 possible answers. Either find the smallest value, and that's the array of the largest sum, or take it one kind of logical leap further, give you an array of size 0, subarray of no elements, I is equal to j, right? What's the implicit sum of no elements whatsoever? 0, kind of by definition, is the identity element for addition. Right? The product of nothing is 1, sort of, almost by definition, right? Anyway, either way is fine. So, but let's just say, if you give me an array of size nothing, the sum of everything in it is 0. If you prefer, solve it that you give me the largest negative value if everything else is negative. Either way, it doesn't change anything. Okay. The algorithm won't change substantially if you do it one way or the other. Okay, any other questions? So, the size of this is arbitrary. It's of size k. And we don't know what k is. K could be anywhere between 0 and n. All right. Everybody happy so far? Yeah, question?
Is the k static number or we can change it?
You tell me what k is. I'm not giving you k. I'm asking you what k is and where does it start, where does it begin to give you the maximum sum.
I mean the k, we can add a number and the k plus 1, or I just define that the k is a static number.
K is not a constant, if that's what you mean. It's a function of, it's a function of the array and the size of the array, right? So for any arbitrary array, k could be 0, it could be 1, it could be 5, it could be 7, it could be 1,000,000, or it could just be n, assuming n is bigger than 1,000,000. It's not going to be larger than n, obviously, because I'm asking for a subarray. The subarray is of size k.
So it will not be smaller than k.
All right, so there's a misconception here. K is not a parameter that I'm giving you. K is a parameter that you're giving me. Okay, so whatever you're giving me, that is k. Okay, I'm not giving you k and you have to match something to k. I'm giving you an array of size n, and I'm not telling you what k is. Your answer will tell me where does this maximum sum subarray begin and where does it end, and the difference between the beginning and the ending is what we're calling k. But k is not a parameter of the problem. It's an attribute of your answer to my problem. Right? Does that make sense? Okay. But I'm glad you're asking questions, because if anybody has a misconception or question or something vague, please ask. Don't hesitate, because others in the class have the exact same question. I mean, experience has shown that if you ask a question, probably a quarter or a third of the class have the exact same question. They're just too afraid to ask. So you're doing your peers a favor by asking. So thank you. All right, what else? Anything? Any other questions about this? I'm not telling. His question was, am I looking for a linear solution for that? If you can come up with one, that will be amazing. But I'm looking for anything less than n cubed and keep working on it until you get it as low as you can. If you get to linear, I'll take a bow and give you even more extra credit. But even if you can get it to quadratic, that'll be nice. If you can get to n log n, that's even nicer and more impressive. But the reason I'm not telling you whether linear is possible or not, because I want you to kind of think about that as well. Right? So if I give you the time complexity, the best possible time complexity, right now, that's a big hint already of what you should try, what you shouldn't try, when you should stop working, when you should continue. I'll leave that up to you for now. Okay. It's part of the meta exercise is to figure out when to stop, trying to optimize it further and further. But let me just say this. Could it be better than n? Like n, square root of n, or n over log n, or log n, or something less than n? How many say it could be less than n, potentially? How many say n is the lower bound? Yeah, you're right. Why? Prove that n is a lower bound for this. You have to check every element. Because why? If you don't check some element, if you don't look at some element, it may ruin your solution. Because if your block has some element that you didn't look at, that element could have been minus a googolplex. And that can't possibly be the answer. If the element that you didn't look at is outside the block, that element could have been a googolplex plus a googolplex. And because you didn't look at it, you didn't know to include it in the block. And that, again, can't be the right solution in the block. How many can see this argument? And that means you've got to look at every single element. Otherwise, you'd miss something that could really affect your solution. Whether that block that you propose as a solution in green is the correct solution or not. That's an adversarial argument. It's like an oracle argument or adversarial argument. But we just proved the lower bound of n. But that's a proof now. Notice that we didn't say, oh, you must look at everything QED and walk away in victory, because that by itself is not a proof. You have to explain why must you look at everything. Because if you didn't look at everything, the following could happen, and it can't possibly be right, and the algorithm must be incorrect in some cases, and that's why if it's not correct algorithm, it doesn't matter how efficient it is. It's incorrect. For an algorithm to be efficient, we may not say this very often, first it has to be correct, and then efficient. Because I can give you a very inefficient algorithm to solve anything you want, right? Assuming it's a discrete problem. And I can give you an incorrect algorithm for anything you want that's very efficient. I can just return 0 no matter what you ask me, and I can do that in constant time. But if you ask me for addition, multiplication, or self-driving car algorithm, returning 0 to you when you invoke me as a subroutine is not correct. It's just efficient. So I'm saying the obvious, but keep that in mind. If an algorithm is incorrect, it doesn't matter how efficient it is, it's still incorrect. And efficiency is not even coming to play. OK. So you just proved an n lower bound. So obviously, don't try to do it faster than n, just as a hint, right? Obviously, because that's impossible. So don't waste your time on that. But you see the power of lower bounds. Why do we prove lower bounds? So that we know when to stop. When to stop what? When to stop optimizing and pushing the time complexity lower and lower and lower. When you reach the lower bound, stop. You won. And that's not completely true at the meta level. Why may you want to continue even though you have an algorithm that's correct and efficient and matches the lower bound with an upper bound of the same growth? Why may you still want to continue to work on the problem? Let's just take this metacognition step. Yeah. Yeah, you may want to push down the constant. Maybe a linear time algorithm, but the constant may be a billion n. That's not a very good constant. Give me another scenario where you may want to continue. You don't want to necessarily walk away in victory. You may want to continue to fight and keep optimizing and improving and making the algorithm more efficient. When else?
Time complexity of the brute force is n cubed. I think it's n squared.
Let's come back to that. There's still a question pending. Yeah. Yeah, maybe more efficient in particular scenarios. Or what else? Like special cases of inputs. Sorting has a lot of that going on. We'll get to sorting in all these scenarios. When else, when you want to continue to work at it, even though you met the lower bound, and it's not going to get asymptotically more efficient? It's not elegant, it's too complicated, it's convoluted, it's 15,000 lines of code. Yeah, then maybe try to find a simpler algorithm. It's also order n, but it's a lot shorter, more easy to understand, easy to explain, easy to prove correct, and so on. So there's lots of reasons you may want to continue to work on a problem, even though you already came up with an algorithm that matches the lower bound in terms of its running time complexity. Okay. But at least you're not going to try to make it faster than that. You're just going to try to make it more elegant, more simple, maybe better for special cases. You know, but there are reasons to continue. Yeah, the questions. Any more questions? Oh, so he's saying, why isn't it n squared? And he's asking the same question. Why isn't n squared the brute force? Well, because you have 2 pointers, I and j, and the 2 pointers basically pick every combination of starting and ending point. How many combinations of starting and ending points are there? You know, there's an I going to a j in an array of size n. How many ij combinations are there? More precisely, it's n choose 2, right? How big is n choose 2 asymptotically? You know, in terms of big O notation. Again, I don't want to be presumptuous. How many know what big O notation is? Big O of n squared. Okay, most are good. So I'm glad. We'll define it anyway, but that's where prerequisites really come in handy. So we all know what big O means. What's this n choose 2? Big O of what? It's quadratic. And for each one of those ranges, you got to add up everything in between. And that everything in between is another factor of n potentially. And so yeah, it is cubic. The constant is not 1, is less. You're right. Constant is smaller, is relatively small, but it's still cubic. Pure brute force. All right. Anything else on this for now? Yeah. Yeah, it'll be a little bit less because if the starting point and the end point are the same point, you can handle it as a special case, but it's still one more case. And if you don't want to look at all those, subtract n from this n choose 2. Because there's n of those cases where I and j are equal. There's n of, how many can see there's n of those cases? I is equal to, okay. So, but it doesn't reduce the asymptotic growth of n squared for the number of pairs, big O. Okay. Good questions, yeah. What, I can barely hear you. Multiple subarrays? Okay, so we're asking for a single subarray, not many subarrays discontinuous. We're asking for a contiguous, one block contiguous of a subarray. Oh, I see what you're saying. She's asking, what if the answer is not unique? Very good question. How many can see the answer may not be unique? Good. In fact, it could be highly non-unique. How many different answers could you have? Up to n, up to theta of n, big O of n, and also omega of n. How many can see there could be n different answers? Yeah, good. In fact, it could be worse than that. Give me a scenario where there's n squared answers all the same. All zeros. If the entire array is all zeros, any subarray will be an answer, and the max is the answer is 0 for all of their sums, and there's n squared. In fact, there's n choose 2 possible answers. Good. Very, very nice insight. So what should your algorithm do then? Well, first of all, it should be efficient. And of course correct, but what answer should it return, do you think?
Starting at any position. This is the
Yeah, so when I asked for a subarray of maximum sum, I didn't ask for the subarray of maximum sum because I knew too that it's not unique. I asked you for an array of subarray block of maximum sum. And if a bunch of things fit that category, what can your algorithm return? Any one of them is fine. I asked for one, you give me one, I'm happy. I got what I asked for. I didn't say which one, or the leftmost one, or the largest length one, or the smallest length one. Or, I asked for a subarray of maximum sum, and if you give me one, we're good. So that's a very good insight. So give me any answer you want, as long as it's a correct answer. Not the correct answer, because there could be many correct answers. Okay. Another way of saying it is, tell me what the maximum subarray sum is, and then give me a subarray that has that sum, and I'm good. Because the quantity itself is unique. How many can see that? Yeah. The actual subarray that has that sum is the quantity, may not be unique, but the quantity itself is unique. Okay. Just like in graphs, when you ask for a shortest path. The shortest path may not be unique. How many can see that? There be many paths all the same length, and they're all different paths. In fact, you run into that with your GPS, with Google Maps or Waze or your navigation system, Apple Maps. You chart a map in your car for navigating, and sometimes it gives you one path or another path or a third path, and it can be many other paths, all the same mileage. Which path should it return? Well, it picks one. It may not be the one you like, but it's one of shortest distance, or shortest time, however it's optimizing it. And that's the one, it gives you a path of the minimum length, and so it's working fine. And you may prefer a different answer, but it gave you an answer and it's correct. The shortest path may not be unique. But now that we mentioned it, if you're constructing a GPS system and there's many shortest paths, which one should you give the user? How would you further optimize? You don't want to give it a random shortest path. If
Other vendors that can take into consideration, per se, the time it takes.
right? So don't just optimize the distance. Within all the paths of the same distance, give it the path of the shortest time among all of those. So optimize on the second quantity. And how do you compute the shortest time for maps and distances? You look at the speed limits and even the traffic in real-time traffic conditions and add up all the blockages in traffic, and now there's apps that do all that for you. What if there's many paths of shortest length and all have the same shortest time? What would be a third quantity that you may want to optimize on? Reduce the number of turns. Or maximize the scenic quality of the route. Give me a route with more trees and less concrete and freeway, or whatever, assuming all other things are a tie. And there's many other things you can do. Now you're seeing there's multi-level kind of optimizations. You can pull in other criteria, and it'd be nice if GPS systems could actually do that. Or give me the path with the greatest number of gas stations and restaurants, or hotels along the path if you're going cross country. That'll be an interesting optimization. And some apps can probably do that now. Okay, all right. But it's good to keep all these things in mind. All right, let's go back to what we talked about last time. So last time, we talked about the halting problem after we discussed the evils of induction. And the halting problem is simply, given a piece of code or an algorithm, does it halt or not halt on a particular input? And we said the halting problem is very tricky. In fact, it's undecidable. It's not solvable by any algorithm, right? And we gave an example of a halting problem involving integers, the 3+1 problem. And then we said it's not about size either. Because some people think, well, longer programs or more complex algorithms, it's harder to determine this halting for them because they're long and complicated. No, that's not why. Because there's very short programs whose halting status was open for centuries. We had no idea whether they halt or not for 10 or 12 lines that embody Fermat's last theorem in these 12 lines of code, or Goldbach conjecture. That's still open after 3 centuries. We don't know if this program halts or not, because if it halts, if and only if Goldbach conjecture is true. By the way, Goldbach conjecture we mentioned is the hypothesis or the notion that every even number is a sum of 2 primes. We haven't found a counterexample to that, but we can't prove for centuries now that a counterexample exists, and we can't prove it in general. So the halting problem is tricky business, and we gave a proof of the halting problem. We said, halting problem, assume there is an algorithm for it, call it S. It solves the halting problem for any program P and input I. And if it does its job, then put it in a larger subroutine T that calls S with P and I being T's parameter. They're all strings. X, P, and I are all strings. The program data, they're all strings, right? So S will tell you whether P halts on I and feed T's input to it. And then when T says, when S says yes, it halts, P halts on I, T goes into an infinite loop on purpose. And if S says it doesn't halt on I, T basically stops right away. And so if you feed T to itself, if you run a program on itself, and both being T, it halts if and only if it doesn't halt, right? And you get a contradiction. And that's a form of diagonalization. If this was a theory class, we'd harp a lot on diagonalization, but it is a technique pioneered by Georg Cantor, who invented transfinite arithmetic, who showed that some infinities are bigger than others. There's countable infinities like the integers, uncountable infinities like the reals, and even bigger ones still. For example, the power set of any infinite set is a larger infinity than the set itself. Georg Cantor proved that, and we can prove it too if we had time, and if this was a theory course, we'd do exactly that. But it's a non-existence proof, and Turing used Cantor's work very heavily, in particular this technique of diagonalization, to prove all sorts of interesting things about what's possible, what's not possible to do computationally using algorithms. Notice that this is not a theorem about Dell computers or iPhones or NVIDIA GPUs or Cray supercomputers. It's a theorem about all of them. It's a theorem about any computer that you can conceive of, as long as it works by executing instructions coded up as a program. And that's a very, very general statement. It's true about any future computer as well as any present computer. A quantum computer can't solve the halting problem either. And we don't even have those yet. We don't even know exactly what a quantum computer might look like. Okay, help me understand this argument. Okay, how many feel a little uneasy about this argument? And if you do, you understand it better than those who are comfortable with it, because if you the more you think about it, the more you try to wrap your mind around it, the more uneasy and uncomfortable it gets. Because this is a statement about every possible algorithm, that not just every algorithm that we ever constructed, every algorithm that we will ever construct, and not just us, but an alien, omniscient, race of beings from some faraway galaxy, they won't be able to solve the halting problem with their algorithms either, and they've been around for 1 billion years, maybe. It's not a matter of smarts. It's not a matter of R&D. It's not a matter of effort. An algorithm doesn't exist for this problem. Not in computer code, algorithmic kind of format. Any questions about that? Because if you're completely comfortable with this, you probably don't understand it deeply enough. Right? You can meditate on this for years and it'll still bother you. It still bothers me, and I've seen this before most of you were born. Yeah.
How about memory constraints and like real execution of those?
Yeah, so we assume that it's arbitrary algorithms, and then when they run, they have as much memory as they need, as they're trying to allocate this memory. We're not saying that there's a constraint on the size of the computer. Yeah, if the computer is small enough, you may not be able to do. If the computer is small enough, you may not be able to sort even, right? Or run a video game or whatever it is you're trying to do. But we allow arbitrary resources, and it's still not possible, even with arbitrary resources. So definitely with limited resources, it's even more impossible than that, if you can say that.
But I was thinking about, for example, the Fermat theorem.
Yeah.
If we had integers of a limited size, we could for brute force.
Oh, sure, yeah. So we're not saying that a special subproblem, a subclass of the problem, can't be solved. If I say A, B, and C, and N are all less than 100, yeah, obviously you can do it. Try all combinations of numbers A, B, C, and N less than 100, and after 100 to the 4th time, which is not that high, it's of 100 million actually, you'll be done. And 100 million for a fast computer is just a few seconds. Yeah, of course. Same if A, B, and C, and D were less than 3. But that's not saying much. This is a general problem. Making it more specific, really cripples the problem. It limits it in such a severe way that it's no longer anywhere near the original problem. But of course, if A, B, and C, and N are less than a googolplex, again, you can do it in finite time. It'll be a googolplex to the fourth. That's larger than the number of, femtoseconds since the Big Bang, 14 billion years ago. But that's still finite. And then all bets are off. The theorem doesn't kick in. Right? So the halting problem is got to solve arbitrary instances of the problem, not just limited finite subset. And that's important. In fact, I have a slide on that too. Right? So it means there's no single algorithm that solves correctly all instances of the problem, not just a finite subset. Why? If I allow incorrectness to creep in, for example, first of all, if you have a limited number of instances, you can always solve it for that limited number by brute force or by yes, no for that limited number, and code all the yes, no answers for that limited set into one big table and just look up the table and spit out the answer. And that algorithm certainly exists. We may not know what it is, but it exists. If you allow incorrectness, all bets are off also. The theorem doesn't kick in if you allow some of your answers to be incorrect. Let me give you an example. I have a very simple algorithm to tell you the time, and sometimes I'll be wrong, but sometimes I'll be right. My algorithm is always to say the time is 5:55. No matter what you ask me, when you ask me, I'll always say 5:55 p.m. So it's a one-line algorithm for telling the time. Now, I'll be correct sometimes. Like right now, I'm correct. Look at the clock there. Oh, what a coincidence. But a few seconds from now, I won't be correct anymore. But I'll be correct how often, if that's my algorithm, to always say 5:55. I'll be correct twice a day. So a broken clock that's not running, that's stuck, is correct twice a day. And that's a very simple algorithm. There's hardly any mechanism inside a broken clock. In fact, you could just paint it on the wall. You don't even need gears and batteries inside. Is that an algorithm for telling the time? No, because it doesn't work sometimes. It only works for a limited number of inputs or cases. And other times, it's wrong. So if you allow incorrectness, the halting problem becomes completely solvable. What's a sometimes correct, sometimes incorrect algorithm to solve the halting problem? Hint, broken clock. Yeah. Always say it halts. No matter what programming input I give you, say it halts. End of story. Just one print statement is your algorithm. Can't be any simpler than that. And you be correct how often? How many inputs would you be correct on? Infinite number. So you're not just twice a day, you'll be incorrect infinite number of times. The problem is you'll be incorrect an infinite number of times too. So it's no big trick to pull off such a stunt. I mean, it's a little clever. Yeah, I grant you that. But it's not really useful. It's not correct, and it doesn't do much. And you're not any smarter for it. So when you have algorithms, not only should you be correct sometimes, or even an infinite number of times, you need to be always correct. Otherwise, you haven't achieved much. And it's easy to do these other cases where you allow some incorrectness. Okay. In fact, even if you don't allow incorrectness, you just allow the algorithm to not say anything in some cases. Just remain quiet. Not be incorrect, just have no opinion whether it holds or doesn't hold. There's also a very simple algorithm to solve the halting problem if you're allowed not incorrectness, just silence sometimes. And you want the right answer an infinite number of times, and you allow it to also be silent on an infinite number of cases, not give you an answer. What's an algorithm for the halting problem then? It's a little more subtle than always saying yes, but it's almost as simple. How would you solve the halting problem if you allow the algorithm to be silent, not give back an answer, an infinite number of subcases or instances or inputs, and you still want to be correct on another infinite number of other inputs? Can anybody think of an algorithm? How would you solve the halting problem, say for the cases when it does halt? For the cases where it doesn't hold, don't say something wrong, but you're allowed to not say anything. One word algorithm. What is the word we're looking for? That's a big hint.
You just run the program and
Run the program. Just simulate the code. Just run it. I guess it's two words. Run it. Or just simulate is one word. If I give you a program and an input, you start simulating it. If it halts, you say, yeah, it halts. And you raise your hand in victory, and you stop, and you give me the answer, and you're right. And you'll be right an infinite number of times for all the programs that do halt. For programs that don't halt, run them. They don't halt. What are you going to do? Keep running them, and keep running them, and keep running them, and you're not telling me anything. But in particular, you're not telling me something wrong. You're just not telling me anything. You're silent. When you're silent, you're not lying. You're not telling the truth, but you're not lying when you're quiet. Okay. There's a big difference between the two. So that algorithm is never wrong, and it's right an infinite number of times, and it's very simple. Just run the code. So that algorithm is basically a compiler. How many see that? Compile the code and run it. Okay. That doesn't make this theorem false of Turing that said the holding problem doesn't have an algorithm, because an infinite number of cases, you're not giving the answer. If you're not giving the answer, you're not correct. You're not incorrect, but you're not correct either. You're just silent. And if you allow silence as an answer, all bets are off. And that's not a very useful thing to do. Okay, if you allow infinite programs or infinite, algorithms, and I'm not even sure what that means, but all bets are off also, because you can solve the holding problem using an infinite if statement. If the program is this, then do that. Else, if the program is this, then do that. And then say yes, if the program is that, then a big case statement or nested if, infinite set of nested ifs will solve the holding problem by hard coding all the answers into it. That program exists, but it's infinite. How many see that? I don't see a lot of hands raising, so I'm not sure if you're following me or just humoring me, but we'll move on. Any questions about this? All right. There's other cases, if you allow infinite running time, whatever that means, if you allow it to run forever, like simulate it forever, and then give me the answer. Well, there's no after forever. Forever is forever. That's why they call it that. Right? You'll never end, and then you'll never be able to do something after you run forever, because you'll never stop running, and there's no such thing as the highest integer. Right? So, any kind of end run you try to do around this theorem that we just proved, by Turing, that the holding problem doesn't have an algorithm, is bound to fail, and it does fail. There's one exception, but it's no longer about algorithms. We said that in our proof, S can't have an algorithm inside, can't have a piece of code inside. But we didn't say it can't have a magical elf that always knows the answer, or some powerful oracle, like the oracle of the matrix that Neo keeps trying to find, or some deity inside that somehow divines the right answer. We're not saying that that's not the case. We're saying that there's no algorithm inside, there's no piece of code inside. Because if there was, you can use that piece of code inside with a larger piece of code that wraps around it, and then the whole thing, T, will be a piece of code, and that can't exist because that leads to a contradiction. But if there was a magical elf or gnome or hobbit, or hobbits probably can't handle this kind of questions, but some magical creature or deity or oracle or whatever your favorite magical, mythical creature is that somehow divines the right answer without even trying, very hard, that can happen. But then if I ask you how to implement what this oracle or deity does in terms of an algorithm, now you're back to the square one. That can't be done. That's okay. And by the way, there's nothing wrong with the problem itself. I don't want you to think that the holding problem is something undefined about it or fuzzy about it. Or, every piece of code either holds or doesn't hold. There's no middle case. It's the law of the excluded middle. There's no fuzziness. So either it holds or it doesn't hold. It doesn't do both. It doesn't do neither. It does one or the other, but not both. So the holding problem is well defined. It's everywhere defined. There's nothing wrong. It's just a Boolean function. And that Boolean function does exist. How many can see that? The Boolean function exists. An algorithm for it doesn't exist. It's a very disturbing situation, actually. And it turns out that's not the only Boolean function that doesn't have an algorithm. Most of them don't. Turing showed that there's an uncountable infinity of Boolean functions, none of which have algorithms. It's a countability argument. The number of algorithms is countable. You can sort them by size, and within size, by lexicographic order, in terms of their codes or whatever. How many can see that? You can sort all the algorithms in one long list, number them with integers, right, or natural numbers, and that makes it countable. The number of Boolean functions is not countable. We haven't proved that, but for now, just understand that or hear that, and if this was a theory course, we'd prove that too. It's not hard to prove. Uses diagonalization to prove that. Cantor did that. So the number of functions or problems that are not solvable for which there's no algorithm is not just this one, and it's not just a countable number. It's an uncountable number. It's amazing we can do anything using computers, actually, because the number of things that we cannot do overwhelms the number of things that we can do by an infinite factor, an uncountably infinite factor. Impossibilities almost everywhere. And that's the theoretical limit on any computer, not just our computers, our Dells and on smartphones and GPUs and Apple laptops and so on. It's a limit about any computer that anybody can conceive, including deities and omniscient races of beings or whatever. That's quite a sweeping statement, a very dramatic situation that Turing proved. Okay. By the way, when do we want to feed a program to itself? Part of this proof was feed a program T to itself. That may seem esoteric or weird or kind of a strange thing to do, to take a program and feed it to itself, make it run on its own source code. But in reality, sometimes you actually want to do exactly that, and it's very practical. When? When would you like to run a program on its own source code? Yeah, if you want to copy itself somewhere else, maybe. Or, let me give you a non-trivial example. Sometimes you want to write a new compiler, a new super optimizing compiler for a language like C or C++. It doesn't matter. You can do this for any language. You can write the new compiler in C, which kind of leaves you with a bootstrapping problem. How can you write a compiler for the language C, write the compiler itself in the language C? How would that work? You're writing a new compiler. You're not writing it for the first time. You're writing a new one, a better one. By the way, why would you want to write a new compiler if you already have an old compiler compiling the same language? There's lots of reasons you may want to do that. Yeah, the new compiler may be more optimized. It may run faster. It may produce code that itself runs faster. Or it may be a new proprietary compiler that you're a new company and you want to write your new compiler that's different from the old compiler because somebody owns the old compiler and you can use it, but you can't really distribute it. You want to distribute your new compiler it could be proprietary, IP, intellectual property reasons or business reasons to write a new compiler, even though already old compilers exist. It could be faster, better, more legally yours than the others. So yeah, you want to write a new compiler. How can you write the new compiler in the same language that it itself compiles? How can you write a C compiler in C? What would happen? Who would compile it for you? The old compiler. But your compiler produced better executables. So once your compiler is compiled with the old compiler, what do you want to do next? Compile your compiler with your new compiler. So you want to feed your compiler to the compiled version of your compiler. Now it's compiling itself, and now it can be written in pure C. It's a bootstrapping process. How many see that? You got to compile it twice, once with the old one and once with itself. Because if you just stick with the old one doesn't optimize very well. It produces very large codes that are not very efficient, machine language codes, and now you want to run it with your super optimized compiler to produce even a better executable version of your own compiler. So yeah, you can feed it to itself. So the scenarios in real life where you feed a program to itself very naturally and for great reasons. So that's nothing strange about that. Another interesting, corollary from this halting problem is that infinite loops are not computable, not detectable. You'll never have a compiler that detects infinite loops because that's like solving the halting problem. So forget about that. And of course, detecting infinite loops is a very interesting practical problem that some of you may have had to solve the hard way during your debugging sessions, grappling with code late at night. You ran into infinite loops and you try hard to get rid of them and find out where they are. And how many have ran into infinite loops in your programming experience? There's pretty much everybody. So that's a very practical problem. Can't be solved. There's no algorithm for it. So when you can detect an infinite loop and get rid of it, you're solving a very specific case of a very hard problem. And now you know yet one more reason why programming is so hard. And avoiding infinite loops is so difficult. You're solving an undecidable problem, or more specifically, a specific instance of a very hard problem. So don't feel so bad next time you run into an infinite loop and you're not sure what's causing it. You're trying to solve an undecidable problem for which there's no algorithm. Doesn't mean you can't solve specific instances. Viruses can duplicate themselves and read their own codes and manipulate their own selves. And of course, in biology and DNA and cells and life, nature has already discovered that something can process itself, right? And things can self-replicate. Nature discovered that too. Computer viruses basically mimic what nature does. And von Neumann studied self-replication very rigorously as a scientific area, and he invented cellular automata, of which the game of life, Conway's game of life, is a special case. Von Neumann did a lot of stuff. He invented game theory, for example. He worked on nuclear weapons. He discovered many theorems and invented whole sub-areas of mathematics. And he also worked on self-replication and described automata that can replicate themselves. So it's a very interesting property for something to replicate itself. If you're not careful, you can run into infinite regress, right, if you think about it. And to show you what I mean, here's an extra credit problem. Write a program that prints itself out, prints out its own source code, and then stops. And by own source code, I mean print itself out exactly, character for character, punctuation mark for punctuation mark, not approximately or with some missing characters. The Unix diff shouldn't be able to tell the difference between what the program outputs and its own source code. How many understand the problem? Okay. How many have solved that at some point? Wrote a program that prints itself out? A few of you. The rest of you, my gift to you. Write a program that prints itself out. And do it without any tricks. That program should not read its own source file, obviously. You just have the executable, and when you run it, it prints its own source out without reading it from anywhere. Otherwise, it'd be trivial, and I wouldn't be insulting your intelligence by giving you that problem of just reading your own source code and printing it out. That's not what we're talking about here. You don't have access to your source code. Question? Yeah. Now I'm putting a bounty on it. Now I'm raising the ante on this. Yeah. So that problem appears in the problem sets. Very good. That means you looked at the problem set. So I'm proud of you. How many have looked at problem set 1? Good, most of you. If you haven't, I'm not even sure what you're doing in this course or even in graduate school. But I digress. Solve the problems. Work on those problems. Work in groups. How many came to yesterday's problem-solving session? Okay, a bunch of you. Good. Was there pizza? Was it? Oh, they ran out of pizza. Okay, but there was pizza at the beginning.
Yes.
It means you got to get there early. That's another reason to be on time. There was pizza there. It just ran out. I guess next time we'll have to order a few more pizza pies. All right, we'll figure it out. That's not a difficult algorithm. But form study groups, solve lots of problems. It's all going to be good. Yeah, question? Good question. Is this true for every language? You do this in arbitrary languages. The short answer is yes. It's not language dependent. There's no dirty language tricks here. Some special command that does, solves it for you. Yeah, you can do this in any language you want. In some languages, it's easier than others, admittedly. But you can do this in just a few lines. This program is very short. It's just a few lines, and if you stick them all together, it's one long line. But it's not a long program. That's not the issue here, and it's not about the language that you're using. Although in some languages, it's more natural to do it than other languages in a short amount of code. So it's not language dependent. Self-replication is humans can do self-replication. How do we know that? Because here you are. I mean, your parents self-replicated, and here you are. Right? I'm not being facetious. It's true. But we're not the only species that can self-replicate. It's not species dependent. Every species can self-replicate. And those that can't or couldn't, they're not here. But there's millions of other species that are here that. So just like self-replication is not biologically species dependent, self-replicating code is not language dependent. Any other questions? It's good questions. So typically when you write code, you can write many lines per hour or even multiple lines per minute. Right? This will be the toughest piece of code you ever wrote in terms of lines of code per hour. Because we're talking about like a handful of, you can count on one hand if you do it efficiently. If you do it inefficiently, you can count on two hands, the number of lines of code. But this will likely take multiple hours. It's very rare that coding can only produce 3 codes in 5 hours or whatever. 3 lines of code. So this program has a very nice, impressive ratio in terms of time per code, per source code lines. I don't want to scare you. If you think about it the right way, it's not all that hard once you see how it hangs together. But it's a very interesting, insightful problem. And by the way, if you've solved this problem before, a few of you said that you solved this before. If you have, do this with a much shorter program than you did before. Try to minimize number of lines of code or characters of source code. Minimize number of characters. Make it fit in a tweet, literally. You can do that in C, for example. You can make this fit in a tweet. How many characters is a tweet? I don't tweet, but we have politicians that do it a lot. You may have heard of some of them. You can do it in 140 characters or less in C. So that's already a big hint. And it's not some it's not some dirty trick about the syntax of C or some special command. Or you can do it in any language. In some languages it'll be a little shorter or a little longer, but it's not a long program. Okay, any other questions? Good question. He's trying to make an end run, as you should, around the logic. And he's saying, is an empty program a valid answer? An empty program, in some languages, an empty program is a perfectly valid program. It would run, it would do nothing, and it prints nothing. So essentially, technically, it prints itself out by printing nothing because the program itself is nothing. How many say, yeah, that's a valid solution? I mean, technically, it's not wrong, but that makes an end run around this whole subject of self-replication for several reasons. One, it won't work in other languages. Right? So, for example, in some languages, like C, in C, can you have an empty program? No. A program has to have a minimum number of characters. You have to have a main, paren, brace. So the shortest C program, I think, is this, technically. That's 8 characters. And that won't self-replicate. So your solution won't generalize to C. So yeah, maybe some languages, your trick will work, and it will work in some languages. But then I would say generalize your solution to other languages, including C, and then that won't work anymore. So it falls in the nice try category, and I commend you for thinking like this. If you ever change your career to law and want to become a lawyer, I'm sure you'll be very successful. That's exactly the kind of thinking you need to do. Kind of make an end run around some situation. But that's not the point of the exercise. But I commend you for thinking about that. So if you've never solved this problem, solve it. If you solve the problem, try to make it as short as a program as you can. And that'll be my gift to you. In some previous semester, my students gave me this this stamp. And so saves me a lot of time sometimes. True story. One of my favorite gifts. Any other questions or comments? Yeah. No, it can't read a file. Because if she's asking, can the program read a file? No, because if you read a file, you can solve it very trivially by going to your source file and reading it and printing it. But I will not waste your time or insult your intelligence by giving you this problem of reading a file and printing its contents. That will be, many years ago in your computer science experience, right? Not in a graduate course on algorithms. So, no inputs of any kind. That's why I say no inputs of any kind allowed, not even reading a file. That's an input. The program only has an output, not an input. Completely self-contained. Right? A DNA molecule doesn't take lots of inputs to replicate itself. I mean, it uses raw materials, but it's self-sufficient. A seed to grow into a tree is completely self-contained. It self-replicates by its very structure. It doesn't look at another seed and copies it. And even if it did, it wouldn't be a tree. So anyway, very good questions, but let's try to not make end runs around this, to trivialize it. I want you to get the deep understanding of self-replication by actually going through. And think about it another way. If you write a program that prints itself out and you do it generally enough, it can have an arbitrary amount of payload inside. You can add extra stuff that it can do besides printing itself out, like erasing your disk or encrypting your disk and telling you should pay in Bitcoin to have your disk unencrypted. That's called a computer virus, and then replicate itself to other machines. And and the source code is not around. It needs to do all that and replicate itself onto other drives and other computers and over the network. And that's exactly what viruses do. They self-replicate, and they also do other stuff. Besides, they have a payload inside. That payload may be quite nefarious. How many have heard of things that encrypt your disk and ask you for Bitcoin ransom and ransomware and also, whatever. So there's a lot of applications of this kind of techniques in computer viruses. And there's an extra credit reading on the website. In fact, this may be required even, that it's an article about self-replication. It tells you some of the nuances and subtleties of self-replication, and he talks about von Neumann and how he studied it and the game of life. And there's even an example of self-replication on a chessboard with a few simple rules. You can have a configuration on a chessboard that self-replicates. And then self-replication involving robots and not just codes. And ideally, you want full self-replication, right? In the movie Terminator, you saw how Terminators self-replicate. They build their factories and produce more Terminators. And in fact, even in the scenario here, I mean, you have most factories now are automated. They have robots that build stuff, cars, and they're all built using robotic arms and robots and conveyor belts. And you've seen the pictures and videos of factories now. They're all mostly automated. Those robots that work in the factory, those big robotic arms, how do you think those are produced? What or who produces those big robots that you have in these automated robotic factories? Other robots. In fact, they themselves produce themselves. Those big if you go to a factory where they produce these big robotic arms, you see a lot of these big robotic arms building more robotic arms that then they sell to other factories. That's an example of self-replication right there. So I mean, it happens all over the place, not just when your parents had you as a child. And then we talked about non-existence proofs. It's not symmetric. Proving that something exists is not the opposite, not the logical symmetric complement of proving that something doesn't exist. You have to cover a lot more ground than non-existence. And Turing's proof of non-existence of the algorithm for the halting problem is exactly that kind of a proof. It's a proof of non-existence, and it's a good day when you can do that. And then there's another article about, speaking of Turing, about hypercomputation and all the other stuff that Turing did that is not as famous as the main things that he did, like inventing all of computer science. He also invented AI specifically and neural nets and did other cool stuff. And it turns out, I'll just mention this in passing, just so that you don't go through life never having heard about this really cool concept. just like the halting problem is undecidable and there's no algorithm for it, even if you can postulate a black box oracle for the halting problem that solves it correctly, and you have a computer now with a subroutine oracle black box, never mind what's inside, like a deity or a gnome or an elf that solves the halting problem for you, now you may think that all the other unsolvable problems become solvable. Because now you have a black box that's so powerful it can do the impossible. Never mind how it does it, it just does. If you had such a device, could you now solve all the other problems that are not solvable? The short answer is no, you can't. These problems are still unsolvable, even if you could solve the halting problem with a black box that has magic inside. There are problems that are still not solvable, even given that. There are Boolean functions for which there's no algorithms, even given a magic black box to solve the halting problem. There's a whole hierarchy of unsolvable problems, each one more unsolvable than the lower levels. There's a countable infinity of unsolvable problems, each one more and more and more impossible. So just like Cantor showed that there's levels of infinity, some are bigger than others, Turing showed that this level of impossibility, some things are more impossible than other impossible things, even though they're all impossible. How many have ever heard of that? My gift to you. I should stamp it again. So, you know, if you haven't heard about it, it's called hypercomputation, and this article talks about it, and read it for fun and profit and credit. And you know, if you want to dive more deeply into it, you know, there's plenty of books on it, and I'll give you extra credit for doing that. So, and of course, if you want to watch Imitation Game, you know, yeah, there's credit for that. And next time, you know, another one of my gifts to you, I want to mention before we end that there are numbers that you may not have heard about. So you all heard about the rational numbers, the integers. This is a Venn diagram, by the way. It's a Venn diagram, set containment diagram. So the primes are a subset of the naturals, which in turn are a subset of the integers, and these green ones, examples of numbers are in this larger set, but not in the smaller set. So the rationals contain fractions that are not integers. And then there's transcendental numbers, and then the reals. And those you all heard about, numbers which we know and love and appreciate. But I want to tell you, at least once in your life, that there are things way beyond that. The complexes you heard about, but there's quaternions, where you have I, J, and K all being square roots of -1, but not equal to each other, and it's not commutative. And then you have octonions that are not even associative, and then sedentians where there's 16 different units. I, J, K, and a whole bunch of others, there's 16 total. They're all square roots of -1, but not equal to each other. And this one is not just not associative, it's not alternative. And I'll leave it to you to follow up on these things. And then there's numbers that are called surreal numbers. How many heard of surreal numbers? All right, there's extra credit reading about surreal numbers. There's a little novella by Knuth. There's also wiki pages about them. Surreal numbers contain the reals. Again, this is all a Venn diagram. So reals contain the reals, but they contain many other things too, including infinite quantities and infinitesimal quantities. They are not zero. Okay, so the surreals subsume the reals. And then outside that, there's even more things. These numbers are called surcomplex. Surcomplex numbers are numbers of the form A and B, A plus BI, where I is the square root of -1. But A and B are no longer just real, they're surreal. Okay, and there's a whole algebra on surreal numbers. And then there's lots of things besides that. Right? There's numbers that are computable, and there's numbers that are not computable, for which there's no algorithm that spits out digits. So for pi, pi is computable because you have an algorithm for pi that spits out digits of pi. That's easy to do. Same for e, same for square root of 2. But there are numbers for which there are no algorithm that spits out their digits. None. It's a countability argument. The number of numbers is uncountable. The number of algorithms is countable. So there's just too many numbers, not enough algorithms. It's easy to prove. If you had time, we'd prove it more precisely. And there's numbers which are finitely describable. All these numbers I talked about now are finitely describable. Pi, e, square root of 2, you know, any one of those. But there are numbers that don't have finite descriptions, never mind algorithms. You can't even describe them finitely. And all these regions are not empty. So some real numbers are not finitely describable, and some finitely describable numbers are not computable. Okay? And for extra credit, try to prove these. It's based on countability arguments and diagonalization. But there's a whole lot of complexity going on that at least once in your life somebody should mention to you. And if I didn't do it, I'm not sure who would. So there you go. My gift to you. So any other last minute questions before we stop? We'll pick up next time. The TAs have hours every single day, as you saw from the calendar on the website. Go to them often. How many are working in groups or forming study groups, beginning to work in groups? Okay, good. A bunch of you. The rest of you, please do the same. And we'll see you next time. It'll all be good.
So last week on Thursday, the attendance sheet did not get around to the front of the table.
Okay.
Yeah. And
Yes.
so
Where's the attendance sheet? Make sure you. I guess there's no attendance sheet today. All right, we'll do it next time.
yeah, but for what to do for the Thursday.
So just send me an email.
Okay.
You'll be fine.
Okay. Thank you.
All right.
He was the guy who said Occam's razor.
Oh,
Yeah, I was here.
I'm proud of you.
Also, I took your theory course, so I have like all the required readings done.
Oh, good. So do more. Do other readings. There's plenty of readings to go around.
So I did.
So the required,
ones,
just
I tried to add stuff, but
just submit a short write-up saying you've done this and whatever. Here's write a sentence or two, reminding yourself what it is. But obviously don't spend time rereading it if you read it, unless you want to, of course.
I mean, I figured I'd.
But read other things. There's lots of stuff on that list. Cool stuff to do. All right.
Thank you.
So one first thing was attendance. The second thing was there's no required right, for us, right? Because anything we do is extra credit. Because when you submit something, it asks you whether it's a reading or an extra credit. Because in the syllabus, there's no points for readings as such, so everything is extra credit. And I think it was written. So are we doing all that as extra credit?
Well, it's extra credit or required, or maybe say there could be an other category. If you do.
For everything we just put whatever's read is a reading, whatever's not read is an extra credit.
Yeah. Whatever's not required is by definition extra.
And one more thing, for the problems, is there a definite way of knowing that you achieved the correct answer or you achieved the efficient answer? I mean, because we cannot go and bug the TAs.
Short answer is sometimes I will tell you. Other times that itself is part of the meta question.
At least the correctness of the solution, is there a way to check the correctness of the solution that we are arriving at? Because sometimes we feel like, okay, we are working in groups and 2 or 3 people agree, but somebody doesn't, and then there's like embargo.
So are you asking?